section 5.2, page 4. So now we're going to talk about properties of integrals. So we've talked about the integral problem consists of the limit of a summation. Well, earlier in the semester, the chapters, the book, I don't know what we want to call it, we talked about different properties of limits. And then recently in this chapter, we talked about properties of summations, which were directly related to the properties of limits. So now we can extend both of those to properties of integrals. What I think is a little easier to start with is this middle one, right? We had said if you ever have the limit of a constant times a function, you can pull it out. If you have a summation of a constant or coefficient times some iteration, then you can pull that coefficient, constant, however you want to word it, in front of the summation and then just calculate the summation that will be multiplied. Same thing happens with integrals. If you had x squared, we just solved that problem at the end of the last video. But what if it was 5x squared? Don't worry about it. Pull the 5 out, find the integral of x squared, and then we can multiply our answer by 5. So basically, we can multiply by a coefficient later on if we need. The other limit one that you're probably most familiar with that we just saw in summations recently was if you have the summation of what can be seen as two separate terms or operations happening to an input variable, then we can just make it the summation of the first term, and whether it was plus or minus, we'll continue that sign, the second term summation. So the same thing happens with integrals. You can have just the integral of f of x dx, and then you can have just the integral of g of x dx. I don't feel comfortable when people refer to it as distributing because this is not necessarily thought of as an operator in that way, even though it is an operation, but we usually just talk about adding and subtracting integrals. Going back to the very first one, we had said if you were ever adding up just like the number 5 from 1 to 10, then it's 5 plus 5 plus 5 10 times. So because it's 10 times, we multiplied by how many times we added that number to itself. Well, the same sort of thing is happening here. If you were integrating from a to b, just a constant, notice we're taking the derivative of x, and there is no x in our integral, then basically we're just finding the area of that between a and b. Well, example 1 in this section, we had a constant function of y equals 3. So we had a height of 3 rectangle. And we multiplied it by its width, which was the range of distance we covered, a to b. So it's just kind of repeating that piece. Couple more properties that we need to cover. First one is normally we're integrating from a to b, where a is on the left side of b. But there is kind of this reversing effect where if you were to integrate backwards from b to a, then because you're going backwards, we need to have kind of a negative notation. And I try to explain it here, right? Delta x was b minus a. But if we do a minus b, that's going to give us a negative number of rectangles. So it's like having a negative width. I'm not sure if that makes sense. If we're integrating from one point to itself, then the area from a point to itself is always going to be 0 distance. And lastly, when you're integrating from some range of x values, a to b, if need be, you could break that a to b into two separate integrals. The key here is that it's the same function, not an f and a g, but you've broken it up at some middle point and then pick back up at that middle point. So I have this curve over here that's going from A to B, and we want to shade everything underneath it. But maybe we just want to shade to some point C, stop, and then start again. I think this one is most helpful when, B is down here, that we're finding the area of A to C, and then if the area from A to B is below, it kind of helps to see it as two separate integrals. And then one last piece pulling this all together. Example 6. The key is that we're asked to write as one single integral. If you're looking at all of the starting and stopping points of the integral, the thing that usually catches most students' eyes is the smallest number was -8, so that's probably where we're starting. The largest number is positive 3. So that's probably where we're ending. And these all just have f of x dx, so that will be in our answer. But you need to justify how you got here. Just because you know the answer doesn't mean you know how you arrive at that answer. What I know is I need to start at -8. Of all these integrals, the only one that starts at -8 is the one that proceeds until we hit 0. So I needed to put that integral first. I am going from -8 to 0. Now I need to start at 0 and go to whatever number's next available. Well, here's starting at 0, and this particular one would go to 2. So that needs to be the second integral in my process of arriving at the answer. But if I start at 2 and proceed to 3, I need a 2 at the bottom number and a 3 at the top number, and I don't have that. But using our property up above, where I'm allowed to switch the order I'm integrating, for me it's going to be changing it from left to right, right? If I'm going from 3 to 2, I'm actually going backwards from right to left. But if I change the direction, I also need to change the sign. So the key was seeing that we change this to a plus when we put the 2 on the bottom and the 3 on the top, so that I integrated from 2 to 3. And I've seen a lot of students say they like to start from -8 to 0, from 0 to 2, from 2 to 3. So you're progressing along this sequence of values to get a final integral from -8 all the way over to +3.